Alright, welcome back everyone. This should be the first video in Chapter 5 that you encounter. I'm making it the first one because I believe it's the most important video in the chapter. Okay? And this video will be all about how to draw what's called a free body diagram. Alright? What I will describe to you is a process, right? Or the method to draw this, right? And this will help you simplify your problems, both in this chapter, in next chapter, and any chapter, any of the rest of the chapters in this course, and in Physics 4B and 4C, right? So this process, this free body diagram, will be your bread and butter for every problem, okay? I cannot stress enough how important it is to get this process down, okay? So, what I have here is a fairly simplistic example problem, right? Some box on a horizontal surface. There are two forces on it, as shown, F1 and F2, and there is no friction, right? Chapter 5, we're not dealing with friction yet. That's for Chapter 6, right? We'll apply the exact same concepts, but we'll just include another force of friction. But again, that's later. For right now, how do we draw a free body diagram? Well, in essence, it's called a free body because we don't necessarily draw the object itself. What we want to do is come up with a simpler way to visualize the problem, right? And by a simpler way, I just mean, well, the first step in this process is to draw the object as a dot. That's it, right? So this block here, we can symbolize as a dot. It doesn't matter if that's a square block, if it's a person, if it's a car, if it's a rocket ship. I don't care. Whatever it is, whatever shape, whatever mass, it's a dot, okay? In these free body diagrams. You'll see why momentarily, right? The next step is we want to draw from that dot, starting at the dot and going outwards in whatever direction, we want to draw vectors. So force vectors is next. Okay, and so in this problem we have two, F1 and F2. In the picture shown, it's showing a rather unusual orientation for the force, being or meaning that the head of the vector is on the object itself. Right? Typically, the vectors are starting from an object and going outwards. Or rather, in F1's case, it's like this. F2 would be like this, normally. So what we want to do in our free body diagram is transpose or translate these force vectors such that they start at the dot and go outwards, right, away from it. So we need to keep the same angles, right? Otherwise, we'd change the vectors themselves. So F1 is at an angle of 70 degrees to the horizontal. I'm going to translate that down, trying to keep the magnitude the same. And now we have the horizontal here, and whatever geometric term that's called, what is that, alternate interior angles? That should also be the same 70. So that's F1, right? It starts at our object, right, our idealized object, and goes outwards. F2 starts at it and goes now directly left, right? Right there. You don't have to put the magnitudes, right, the values, in your free body diagram. In fact, you don't even have to put the angle values. I did in this case because it'll help us later on to find components, okay? So thirdly, once you've written out and drawn all of your force vectors on your dot, right, the third thing to do is make sure you have, well, axes. So we can say our coordinate axes, both x and y, and if there's a third one, z, right? So just, you don't have to draw it necessarily in this diagram, right? What I mean by draw a coordinate axis is just specify off to the side which direction you want to be your positive x and positive y. Okay? And that's completely up to you, right? I chose the conventional left and up as positive. Depending upon your problem, right? Depending upon the vectors, you can choose, well, say right and down, right? As plus x and plus y, right? Or say left and up. Completely up to you. If you really want to throw your brain for a loop, you could, well, as an exercise, you could say, wait, no. You could say, that's x and that's y, right? If you think about it, these axes being labeled as x and y are really just aren't official, right? We come up with them. They're man-made. So it's just a convention that horizontal is x and vertical is y. Anyway, I digress. Choose your coordinate axes, right? So off to the side, right, in the same area, just draw plus x and plus y, okay? Next, we need to choose an acceleration direction. So if this object were to accelerate, right, we don't know if it is in this problem or not, but say, excuse me, say for a free fall problem, right, from last chapter, a projectile motion problem, well, the direction of acceleration would be down, right? The gravitational force would be pulling it downwards. So you would draw a tiny arrow down, okay? In this case, we don't necessarily know if it will accelerate or not. So I'm not going to draw the acceleration on the free body diagram, okay? So I'll say, if known. I'll say that. All right. And lastly, or fifthly, if you will, we need to write out separate second law equations, right, for x and y, okay? So what I have written are just the normal vectors, or I shouldn't say normal. What I have are the regular vectors, f1 and f2. We need to break these up into components, okay? And so you can do this on the same free body diagram, or you can do it to the side as another one with just components, right? For lack of space, I'm going to do it on the same diagram. So there is my f1x, and f2 is already in x direction, so that's the same. If you want, you can write equals f2x. It's the same thing. In the y direction, I'll do it in red. We can write that as f1y, and then f2y is 0, so I'm not going to write it. Okay? All right, so once you have those 5 things, and your vectors split up into their x and y components, right? Now it's time to write out the equations. And this should be a relatively straightforward process, right? We know all parts to do this. So what I mean is that for the x direction, we want the net force in the x direction. So F net in the x. Yes, I know that's redundant, what I've written a little bit. The net force always equals mass times acceleration, right? But what are the constituent forces that create that acceleration, right? The net force is composed of what? Well, in this case, it's composed of the F1x force and the F2 force, right there. Those are both in the x direction. One is positive, one is negative. So our net force is the combination, is the sum, if you will, of those two components. So F1x vector plus, I'll leave it as F2, right? Notice I'm keeping it in the vector form, and so I have a positive sign there, a plus sign there, okay? And that's all the forces in the x direction. So the total force equals mass times acceleration in the x direction, right? Don't forget to specify a x. Now let's do the same thing for the y direction. The net force in the y direction vector. Well, oh, you know what? If you've been screaming at your computer, good for you. I actually forgot a force in this case, right? If you've read the chapter, which you should have by now, if this box is resting on this surface, there's another force counteracting F1y, right? There's a force going up, the normal force, right? The normal force is going up. That has to counteract. That's the equal and opposite force to F1y. So that is positive. Why is it positive? The normal force here is positive because that's in the same direction as the plus y direction I specified earlier. So in my equation, that has a positive sign, Fn, and, well, for right now, I'll write F1y as a vector, and that all equals ma in the y direction now. Vector, vector. Okay? And so these are the second law equations right there. And these are the equations you'll algebraically solve, okay, to get whatever final answer you want, right, or whatever the problem wants. In this case, we can solve for the acceleration if you want, okay? What acceleration would this block have? I'm going to change out, right, take the vectors away and add in these signs now, okay? So I'm going to take that vector away and make that positive. F2 is a negative, right? It's in the negative direction. F2 is in the negative direction. It's going left because we've specified the positive x direction to be to the right, right? And again, you are completely free to choose whatever direction to be positive that you want, right? Earlier, I could have just as easily chosen left to be positive. If I would have done that, then these two terms would be switched, okay? So if you choose a sign convention here, you have to stick with it over here, okay? So let's change the goodness, excuse me. Oh, man. I need some water. Let's choose the signs over here. So the normal force would be positive. F1y is negative because that's going down. Okay. Take those off as well. The acceleration in the y, we can already cancel that out. That equals 0. Right? And we can solve for ax, right? This is the acceleration that this block would have. So in that case, F1x minus F2 divided by mass, right? That will equal the acceleration. Do we know that? Well, we do. F1x is the magnitude of F1 times cosine of the angle. So cosine of 70. And we're subtracting F2. All right, so let's plug in some values here. F1 is 59 newtons, and I'm leaving out units for brevity's sake. Cosine 70 minus F2, which is a magnitude, there it is, of 33 divided by the mass of 7. And this actually should give you a negative 1.83 meters per second squared for the acceleration. And this means since it's a negative number, this box will accelerate to the left, right? Because we chose right to be positive. Okay? So this was how you draw a free body diagram. Go through each of these 5 steps for every problem. Okay? Once you get your components drawn out like I have here, your equations should follow straightforwardly from that, and then it's just algebra to solve for whatever the problem wants you to solve for. Okay? So, again, I hope you find this video helpful. Thanks for watching.